All right, so now that we know how to write an ionic equation, we're going to do a little bit of practice with net ionic equations, which isn't much more difficult. So let's just have a quick reminder. See how in these ionic equations that we have provided for us, all of the compounds are in their ionic form because they are ionic compounds in aqueous conditions, right? And that means that we have lead ion here with nitrate ions, potassium ions, and iodide ions. Lead is coming together with iodide to form the lead iodide compound, which is insoluble. And how do we know it's insoluble?
Well, it says it's insoluble.
That's right. It does say it's insoluble. And sometimes that information is provided for us in the chemical equation like that. But is there another way we can tell whether something's going to be soluble or not?
Yeah, the rules.
What do you mean the rules?
The solubility rules on the back of the periodic table.
That's right. So let's take a look at those rules here for a second. All right, to remind ourselves, we have these rules that indicate whether a compound is going to be soluble or insoluble. So lead iodide is insoluble. Which rule says that lead iodide is insoluble?
Rule 3 says that chlorides, bromides, and iodides are generally soluble, except, and lead is one of the exceptions.
That's right. Very good. So, what are our spectator ions?
Spectator ions?
The spectator ions are the ones that aren't doing any chemistry, right? Chemistry is where something changes from the reactants to the products. And you can see here, nitrates, for example, are the same on the left and on the right.
Oh yeah, and the potassium ions.
Very good. So those are our spectator ions, and what's left would be our net ionic equation. That's pretty easy, isn't it?
Yeah, that's easy.
All right, so I'll let you finish up the next two at home. Push pause, finish them up, and then when you're done, go ahead and move forward. All right, let's see what the answers are. Any problems with that?
No, I think that's pretty straightforward.
Okay, good job. Now, I'm going to introduce to you a new kind of compound. Let me redraw the compounds that we kind of have already in our repertoire. All the compounds that, O-U-N-D-S, all the compounds that we have been introduced to so far. We have ionic and molecular. We recognize ionic compounds because they're made of ions, right? That's kind of a boring definition though, ionic, made of ions. But we know what that means, so it's okay, it's not bad. We can usually recognize them because they almost always have a metal. Contain a metal and non-metal, right? Combination. Whereas molecular compounds, what?
Just non-metals.
Very good. Only non-metals. Now, we could also write down here ionic compounds. If they're soluble, they will dissociate. Dissociate. All right? Now, what does dissociate mean?
Does that mean dissolve?
Well, it does mean, you can't dissociate if you haven't dissolved, but dissociate is a little bit more than dissolving. Remember that?
Not really.
Dissociate is what ionic compounds do when they dissolve. That's what we've been talking about here. We talk about how an ionic compound like barium chloride, when it's placed into water, or when we write something like barium chloride aqueous, which means in water, what we're really indicating is that the barium ions are completely separate from the chloride ions. And some chemists like to say, in a solution of barium chloride, there's no barium chloride, because what you have is barium ions and chloride ions. Okay? So, and that's important to remember. Okay? So, ionic compounds dissociate, molecular compounds don't dissociate. However, there is a small class of molecular compounds that when you put them into water, they dissociate. And so they are their own little subclass of molecular compounds, and they're called acids. Acids. So they dissociate and release. When they dissociate, one of the ions that they release is the H plus ion. They dissociate and release the H plus ion. Now let's bring the periodic table up here for a second. You've probably done some homework problems where you talk about the solubility of different compounds. And in one of the rules, the first solubility rule, do you have your list with you there? Your solubility rules?
Yeah.
What is the first rule about?
It's about group 1A.
Yeah, that's this first column here, right?
Yeah.
All compounds that contain these metals, lithium to cesium, francium, are soluble when placed in water. Okay, all group 1A. Now, those are alkali metals, it says. It says all compounds that contain alkali metals, group 1A. However, it doesn't necessarily refer to anything about H+. But what we're introducing to you now is that when compounds contain H+ ions as kind of like the metal ion, so the cation in front, so for some examples are HCl, right? When a compound like HCl exists, where you have, again, your hydrogen ion in front and your chloride ion afterwards, then this compound will dissociate in water to form the ions H+ and Cl-. And an acid is one of these molecular compounds that dissociates, and upon dissociation releases an H+ ion. Okay? And just like we had strong electrolytes, do you remember what the difference between a strong electrolyte and a non-electrolyte was?
I can't say that I do.
All right, so a strong electrolyte was one of our ionic compounds that when you put it into water, it completely dissociates. All right, so NaCl is an example of a strong electrolyte. Okay, but any compound on our solubility rules that is completely soluble would be considered a strong electrolyte. Okay, something that's not soluble, like silver chloride, right? That's one of our compounds that we know is not soluble. It would be an example of a non-electrolyte. All right. Well, just the same way you have strong electrolytes, compounds that ionize when placed into water, dissociate when placed into water, and non-electrolytes, compounds that do not dissociate, do not ionize. There are strong and weak acids. Acids that, when placed into water, completely dissociate, and some acids are weak, where, in other words, you put them into water, but only a small fraction of them will ever dissociate at one given time. And once the dissociation occurs, those two dissociative products come back together relatively quickly. And so here we have written HCl dissociating into H+ and Cl-. And here we have the weak acid, HC2H3O2, dissociating into its product, which are the H+ ion and the C2H3O2- ion, or the acetate ion. So this here is acetic acid. Notice also there's another way that people like to write, chemists like to write, the dissociation of acids. And this way is including a water molecule. And this is done because when that H+ ion leaves the acid, it is going to be associated with a H2O molecule, a water molecule, and the result is this H3O+, which is called the hydronium ion. So in a way, the hydronium ion is really just representing this H+ compound, or the H+ ion, a hydrogen ion. And we have a couple of ways to refer to, therefore, the dissociated proton or dissociated hydrogen ion. It is either a hydrogen ion. We can refer to it as a hydronium ion, meaning that it's just interacting with water, which is what all ions do in solution. They're going to be surrounded, interacting strongly with water. And there's another term which we say it is just a proton. A proton. Now, people sometimes think it sounds funny that we call the hydrogen ion a proton, but if you think about first just a hydrogen atom, do you know how many protons a hydrogen atom has?
1.
That's right. How many electrons does a hydrogen atom have?
It has 1 also.
Very good. So there we go. That's my little model of the hydrogen atom, proton, and an electron. Now, what happens if I try to draw this species, H+?
You add 1 electron.
Add 1 electron?
Oh, no. You lose an electron.
Very good. You lose an electron. So if this species up here loses an electron, what's left?
Just the nucleus.
That's right. And what's in the nucleus?
Just 1 proton.
That's right. That's why a proton, or the proton, is another way to refer to the H+ ion, or the hydrogen ion. So we have 3 different terms that we can use to refer to this hydrogen ion. It's the hydrogen ion. You can call it a proton, or you can call it a hydronium ion. Okay? So you want to be familiar with all of those different terms. The hydrogen ion, proton, or the hydronium ion. Okay, very good. Now, it's also a good time to introduce what we call bases. Bases. So the definition of an acid, a compound that when placed into water, it dissociates and releases the hydrogen ion. The definition of a base is a compound that when you put it into water, the other half of a water molecule results. So we have the hydrogen ion, right? The other half of the hydrogen ion would be what we call the hydroxide ion. In fact, if those two come together, do you know what we get?
H-O-A-O. Water, H2O.
That's right. H2O. You get water, okay? So this is the acid, and that portion is the base. So an acid is a compound, you put it into water, and H+ results. A base is a compound, you put it into water, and the hydroxide ion results. And there's 2 ways that you can get the hydroxide ion. Either from a strong base, and that's like these up here, where you put a soluble ionic compound that contains the hydroxide ion. Okay? Now, not all compounds that contain the hydroxide ion are soluble. Where's our solubility rules? Let's bring them up here so you can see. Rule 6 talks about the hydroxide ion.
Rule 5, you mean?
Oh yeah, Rule 5 there talks about the hydroxide ion. And it says they're insoluble except for group 1A and those of calcium, strontium, and barium. So those are examples of compounds that when placed in water, they'll dissociate and release the hydroxide ion. And this release is a base, right? Because, therefore, the resulting solution contains concentration of hydroxide ion. Another way, though, the other way that a base will behave is in the form of what we call a weak base. Some bases, they do not contain the hydroxide ion to start off with, but they interact with water and remove a hydrogen ion. And that hydrogen ion goes with that base and results in the hydrogen ion with the base with a positive charge and leaves behind the rest of the water molecule, which is the hydroxide ion. Okay, so these are the types of bases: a strong base and a weak base. Most weak bases are nitrogenous bases, meaning they contain a nitrogen. All right, we'll see other examples of this as we move forward, but generally some compound, and I'll put R as an example of just some amount of a compound with nitrogen on it and then there's a number of hydrogens, and we're told this is going to behave as a weak base. How is it going to react to release the hydroxide ion or result in the hydroxide ion? And we need to remember, if it's a weak base, then it's interacting with water, and you're getting an extra hydrogen there and that positive charge, and resulting in an OH minus. Let's be a minus up there. There we go. Okay. Another component that we include on anything that's weak, a weak acid or a weak base, is a second arrow. That's a way to help people realize the forward reaction occurs, but so does the reverse reaction. That's a handy way to help people recognize a weak acid or a weak base. Okay, good job.